Hey, what's up, guys? This is Chung. So today, let's take a look at this LeetCode problem 1062, longest repeating substring. I think this is like a good interview question. Why is that? Because the description of the problem is easy, but it can have a few follow-ups. So you're given like a string, and you need to find out the length of the longest repeating substrings. Return 0 if there's no repeating substrings exist. So what does the repeating substring means? It means that any substring, as long as it appears more than one time, then it's counted as a repeating substring. So let's take a look at a few examples here. So first one, A, B, C, D. Each character only appeared once, which means there's no repeating substrings. In example 2 here, AB appeared twice, and BA and BA also appear twice. So that's why the longest repeating substring, for example, 2 is 2. So and for example number 3 here, we have a AAB and then AAB and AAB. Okay, and so AAB repeated like 3 times. That's why the length is 3. The last one is kind of interesting. Basically, there are like a few like repeating strings. So they're like a, right? So the a repeat like five times, and AA repeat 1, 2, 3, 4, repeat 4 times, right? 1, 2, 3, yeah, and A 3 times, A 2 times. But since we're looking for the longest one, that's why we are returning a 4 here. Okay. Mm, so first, I think uh, a naive way or like a more intuitive thinking would be so let's find out all the substrings. Okay. We just find all the substrings, and then every time when we have a new substring, right, we store that substring into a hash table. And the next time, right, when we find every next time when we have a substring, we check, okay, if this substring has already been seen before. If it did, then we just update the length. Okay, and in the end, we simply return the biggest length. Okay, uh, cool. So okay, let's try to code that first. Kind of brute force solutions here. Uh, that's gonna be I'm gonna have like substring. Okay, sorry about my in, input here. We're gonna have a substring set, okay, and we're gonna have an answer equals to 0, right? So how do we find all the substrings? We just need to have like a 2-pointer, right? We have a first pointer is like I'm gonna have the j, okay, j in and like j in range s, sorry, range n, right? And then I'm gonna have like a actually, so I'm going to have like I and j. So basically, I'm going to find all the possible I and j's that can form a substring. That's why I'm going to loop so the outer loop will be j, okay, and the inner loop will be what? I in range uh, j plus 1, okay? That's how I like I iterate all the substrings, basically all the combinations of I and j, okay, including the letter itself. Okay, so when in case of there's only one letter A here, that's why I do a j plus 1, so that I'm sure I can at least I can also include the one letter case. Okay, Now we have a substring in this case, right? So the substring is going to be the s from I to j plus 1. So that's the substring we're going to get from this nested for loop here. Okay. And yeah, and if substring, okay, if substring, maybe this, okay. If substring is not in the substring set, okay, then we simply add it. We simply add that substring set add substring, okay. Else, right? Else what? Else we simply update the answer, okay. We update the answer with the current length of substring, okay, right? And then in the end, we simply return the answer, okay. So this should just work, okay. Let's try to run the code here. Substring set. Oh, here, yeah, lowercase. Accept it, run it. Cool. See, at least this one is success, right? So I think the idea, the brute force or the first solution is pretty straightforward. Basically, the only things you need to come up with the how can you find all the substrings, right? In in a string here. Basically, the way we're finding it, we use a nested for loop here. Okay, the outer loop is the ending point, right? And the inner loop is the starting point. That's how we find all the substrings. And then basically every time we have a new substring, we check if if it has not been seen before, then we just add it. Otherwise, this one is a repeating substring. We just update the length. Okay. So as you guys can see, the running time is not that good because, so what's the time complexity? Okay. Uh, so the time complexity is so we have an n here, right? So it's a n times n times times n here. Basically, there's another n here since the slicing in Python is also n. I think it's basically it's n cubed. Okay. And the space complexity is also how many substrings do we have? We have like n square substrings in total, right? And then let's see. We have n square substrings in total, and each substring is the length of actually it's n with 1 to n, right? So I think it's something like n cube as well for the space complexity. And that's why it didn't run very fast. Okay, so that's basically the brute force. And if you come up with these solutions at the interview, one of the interview, of course I think you passed the first step. Then the next thing the interview will definitely ask you is, can you improve this time complexity? Okay, so the answer is always yes, right? And how can we improve it, right? If you look at this one, basically it's asking you to find the longest repeating substrings, right? I mean, every time when you have like a mm, it asks you to find the longest, right? Either the smallest or biggest, Another thinking another thinking way is to think of like a binary search. Okay, and when it comes to this problem, we can just use the binary search to search the answer directly, right? I mean, the essence, right? The nature of the binary search is we just directly search the answer itself. Okay, and I have posted a few videos about the binary search, and if you guys remember that, the template of the binary search is that we need to have like a helper function, right? We need to have a helper function, and then that helper function will, basically will tell us if we need to go to the left half or the right half. Okay, so let's try to code that binary search solution here. Okay, mm, for the binary search, we always need to have like a left and the right. Okay, so what's the left? The left bound is basically 0, which means there's zero repeating. There's a zero length of the repeating substrings. Okay, how about the upper bound? The upper bound is the length. We have n here. N equals to the length of s. So the upper bound is n minus 1, right? So I think this is not. It's pretty should be kind of easy to come up, right? So basically, we cannot do n, right? Because if we do n here, it means that there will always be only one string for the entire string, which means it's not possible to have a repeating length with the same length of the string itself. So the maximum one has to be n minus 1, just the same as this example 4 here, right? So in the example 4 here, the length of the string is 5, but the longest repeating substring is 4. That's why our search range will be from 0 to n minus 1. Okay, and then I'm gonna try to finish the template here. So right, okay, left equals to sorry, middle. We're gonna have a middle, and gonna be the left plus right minus left divided by 2. Okay, so the reason we're doing this is we are trying to avoid the overflow, right? If we do a left plus right and divide it by 2, if the left and right is very big, so left plus right could give us an integer overflow. Okay, and then if right, if the helper, okay, I'm just going to call it helper here, but I'll change the name here later. Basically, we're gonna have a helper function, and then we pass the middle here, right? Basically, if the helper function is true, okay, remember, we're searching the answer, okay, and we're looking for the longest. The longest means the biggest, right? Basically, if this thing is true, okay, so what does it mean? It means that, with the current, the middle point here, okay, we know, we find it satisfies our conditions. So which means that, the middle point should be the number. The middle could be our answer. But since we are looking for the biggest one, so that's why we need to assign the left equals to middle here. Okay, and else right equals to middle minus 1. I think here's the template you guys need to remember. Whenever we're looking for the biggest number, we need to use we need to assign the left with the middle. So why is that? Because basically we're trying to move the left one to the right side, keep moving to the right side until we cannot move it forward. Until we cannot move it anymore, and then we know we find the biggest number. Okay, and in contrast, if we are looking for the smallest number, okay, if we're looking for the smallest number, then if the helper function is true, instead of left equals to middle, we will do a right equals to middle. Okay, and then same thing for the else here, we're gonna have a left equals to middle plus 1. Because, when we're looking for the smallest value here, we're trying to move the move the right one, I mean, to the left until we cannot move it further anymore. Then we find like the smallest number. Yeah, just remember this. Yeah, and try to understand why we're using a left here. Because so first, right? So first we're looking for the biggest number. So for the biggest number, right? And we're trying to move to the right side. That's why we set the left point, right? So we know, okay, and because we know we will be moving to the bigger to the greater part. Basically, we're moving to the right side so that we can find a bigger number. But since the middle could be our answer, that's why we do a left equals to middle. And remember, every time when you have a left equals to middle, you know you need to do a right minus left plus 1. So why is that? Because in case you have a left equals to 3 and the right equals to 4. Okay, so for this case, if we don't do a plus 1 here, the middle will become 3. And this helper function is true. It means it will assign the left to 3 again. Basically, this will be a infinite loop here. Okay, it's going to be an infinite loop if we don't do a right minus left plus 1 here. So basically, here's the template. Every time when you have a left equals to middle, do a left plus 1. Yeah, just remember this. Okay, and then in the end, we simply return the left. Actually, is either left or right is fine because when the while loop is finished, left equals to the right. Okay. Okay, so that's how we do a binary search. Okay, to find the longest one. Now the question is how how do we implement this answer here? How do we implement the helper function? And so what are we trying to verify here? Basically, we're verifying with the middle. Remember, this middle one is the longest, is the length of the repeating string. And basically, we're trying to find repeating substring with the length. That's the our helper function here. Okay, it means that with this repeating with this length, can we find a substring, a repeating substring that has this length? That's what we are trying to verify here. Okay, and so a naive way is how can we find a repeating string of this length, right? So I think the easiest way is gonna be a sliding window, right? And we're gonna have basically build like a sliding window of size length, and then we're trying to move the sliding window forward, right? And every time when we move a sliding window to a new position, right, we have a new substring of this length, and then just similar like this one, we're gonna have like a set to store all the substrings with this length, and then if we have seen the same substring already, we simply return true. Otherwise, in the end, we return false. Okay. Cool. So let's try to code that things here, and we're gonna have a scene equals to set, a scene set, right? And then we just loop through I in the range of it's gonna be n minus length plus 1. Okay. So that's the biggest starting point we can get, right? So why is that, right? I think it's kind of easy, right? If we have a like A, oh, it's so ugly here. A, B, C, D, E, and F. Okay, let's say our length is 3. Okay, so we start from this position, and the last position is D here, right? Because we need at least 3 letters to form with this length of string, right? A substring. So that's why we do a n minus length plus 1, so that we can stop at this index. Okay, and yeah, so same thing here. Substring equals to what? Equals to the s from I to the I plus length. Uh, yeah, so that's going to be the substring. And hmm, if the substring is insane, okay, we simply return true, and then don't forget to add this substring to the set here. Okay, and if none of those happens, we simply return false. Okay, yeah. So let's try to run the code here. Submit. Cool. As you guys can see, this one is it's much faster than the previous one. So why is that, right? I think because we're using like a binary search. So let's take a look at the time complexity for the second solution. You know, the binary search is always log n, right? So we have a log n for the while loop here. And then what's the complexity of this our finding method here? Basically, we have a hmm, let's say this one is L, okay, and the first one is the n minus L, okay, n minus L times what? So the time complexity of the slicing here is L, okay, so that's our time complexity here. Yeah, so log n times n minus L times L. I mean, if the L is very small, then the time complexity is going to be close to n log n. Okay, and if the L happens to be the half of the n, if the L is pretty big and it's somewhere close to half of the n here, so uh, so here will become to like a n square, right? And that so for the worst case, we're gonna have like a n square uh, log n. Yeah, because here it's gonna be a 2n times 12n. Yeah, gonna be a 4 n squared divided by 4. So it's gonna be a n squared log n. Yeah, at least this one is faster than n cubed, right? That's why the second solution is much faster. And then this one is always it's the worst case. And for the best case, it's even faster. It's just n log n. Okay, cool. So that's the second solution, right? I mean, Oh, how about the space complexity, right? So the space complexity is gonna be same. mm, So we're gonna have like a scene here, right? So every time when we have like a scene here, we're gonna create like a set, and and the size of the substring is L, okay? And we will have like n L times n, okay? So this is the space complexity because we're gonna be reusing this scene here, okay? Cool. So, and can we do a simple, we can do a simple improvement. I mean, not for the time complexity, but for the space complexity, Instead of saving storing the string itself, we can store in a hash value of the string, right? That can save that can remove the L here, which makes the space complexity to O of n, okay? And we just need to add a simple line here, okay? Basically, we're gonna have a hash equals the hash of the substring. Okay, and then instead of checking the substring itself, we simply check the hash here, and also we add the hash. Okay, yeah. So this should also work. Let's try to submit it. Yeah. So that's a simple improvement. If the interviewer ever asks you to improve to make a further improvements on the space complexity, right? You can just use a hash. Cool. I mean, so now, I mean, if you guys are applying like a regular or normal companies, I believe this binary search solutions should be enough. And but if your guys go is one of those top companies, for example Google, uh, just stay with me a bit longer. I'm gonna introduce uh, a better way of doing this uh, hashing. Basically, we're gonna using a rolling hashing mechanism to basically to further improve this this hashing mechanism to from the best case n and worst case n square to strictly O of n time complexity. Yeah, again, if you guys like, I think if you guys don't really want to dig to the bottom of this problem, you guys can probably stop here. I mean, I believe if you interview Google, I mean, even you even you have gave this kind of binary search solutions, I mean, the interview might still ask you, can you improve this part, right? As you guys can see, basically the bottleneck for this like the solution is the every time we're doing a slicing here, right? So when we do a slicing here, I mean this slicing is depends on the length, right? It will be pretty like time consuming, right? For example, when the length is pretty big and when the n itself is pretty big, right? And then this thing will be like a O of n. Okay, so how can we further improve this one? We do a rolling hash, right? So the idea of rolling hash is this. Let's say we have A, B, C, D, E, F, G, okay? And let's say the length is 3, okay? So at the beginning we have our our sliding window, right? The sliding window is from here to here, okay? So the idea of rolling hash is now the next step we move the window to here to B C D. Okay. If you look closely, actually all we did was we removed the letter A. Okay, we removed the letter A from the sliding window, and then we add the letter D to the sliding window. Actually, every time, no matter how big, or sorry, no matter how long the sliding window is, every time all we need to do is we just need to remove the first letter and add the second letter. Sorry, add the last letter. But how can we? I mean, if this the array is an integer, that will be much easier, right? We simply just remove the value of the a, and then we add the value of d. We keep everything in between, right? That will be much easier. But since this is a string here, how can we do it, right? I think I already told you guys we just need to convert the letter, right? We convert the letter into a number, but that's not enough. So why is that? Let's say if if the number is like a is, let's say the 0, okay, 0, 1, 2, 3, 4, 5, 6. Yeah, basically we just we just use the positions, right? The relative positions uh, of the ASCII code of each letter to convert it into an integer here. So if we're only using, if we're trying to add those numbers together, right? Let's see, and we have a, b, c, and d. So the value of a, b, c will be 3, okay? And yeah, basically, if our hashing method, basically we're implementing a hashing function here, right? And basically, if our hashing function is simply adding the numbers here, that's gonna be it's very easy to have a hashing collision, right? For example, right? If we have a BCD here, the total of BCD is 6, right? But the G itself is also 6, right? So the hashing value of the BCD and G, they're the same. So it's very easy to have like a hashing collision. So I think one of the simple hashing mechanism here is we do this, right? We do a what? Since we have like 26 characters in total, right? So we're gonna use the 26 as like a factor. Basically, we're gonna use a uh, uh, polynomial hashing function. Basically, we just do a like the letter let's say for the letter B, C, and D, right? We do what? We do a number of the B is 1 times 26 of the length of to the power of the length of the letter plus the second one is 2. 2 times 26 dot sorry, so here it's going to be 2. 1 plus 3 times 26 to 0. Okay. And this is the one of the hashing function we can use. Okay. And let's say we move the sliding window from BCD to CDE. Okay. So how are we going to change this hashing function? Okay. Basically, the next one is going to become to what? Become to I'm going to write it in this way. Going to be 2 to the times of 26 equals to 2, right? Plus 3 times 26 to 1 plus 4, right? 4 times 26 to the power of 0. I intentionally write this the second state at with at this position here, right? So with CDE, the hashing function will be 2 times 26 to the power 26 square plus 3, which is D times 26 plus 4 times 26 to the power of 0. Okay, so how can we convert our hashing function from this one, from the first one to this one? Okay, assuming we have a h here. Okay, assuming we have a hashing function here, how can we convert the h from this state to the second state? Okay, so here's the transition function. We just do a h times 26. So every time when we have a new state, we just use the old hashing function. Okay, old hashing values, and then we do a times 26. So after time multiplied by 26, uh, we'll have 3, 2, and 1, right? So as you guys have already found out, these parts are the same now. Okay, so after multiply by 26, all we need to do is we just remove the first part, which is the 1 times 26 of the length. Okay, and then we add the new number, which is 4 times 1. So because the 26 plus the power to the power of 0 is always 1. Okay, new h, okay, equals to this, right? So we can just use this one to keep updating our hashing functions. And as you guys can see, this is like O1 time, because we're only removing the first part and adding the last part. So there's no linear scan here. Cool. So I'm going to implement this hashing function real quick. Okay. All right. So like I said, the first step first, we need to convert convert the strings into numbers. Basically, we're gonna have a numbers equals to that, right? So like I said, I'm going to convert all the letters to its relative positions to the ASCII code. Okay, and ordinal of C minus ordinal of A, right? For C in S. That's how I convert that. So now let's see. I'm going to comment out this thing here. Okay, I'm going to also. So now the H at the beginning is 0. Okay. So first, let's calculate the starting hashing, right? The starting hashing is this, right? So basically, for I in range of length, okay. So how can we calculate the hashing? The hashing is this, right? Equals to a hashing times 26 plus nums I. Okay, that's how we calculate the initial state, right? Like I said, the first one is like is 26 is 0 times 26 of 2 plus 1 times 26 plus 26 power of 1 plus 2 times 26 uh, of power 0. Okay, and every time we just do a multiply by the 26 and then we plus the current number. That's how we calculate the initial hashing values. And then since we have already calculated the first substring, all we need to do is the okay, oh sorry, so since we already have like the first hashing, we just need to add the hashing to the scene, the new hashing, and then I in range 1 to n minus length plus 1. Okay, so why is that? Because we have already calculated the first substring. That's why we can start from second substring here. Okay, and like I said, so the new hashing function, it will be what? Uh, like I said, we multiply by 26, and then we will be removing the first part, the first um, letter, which is the nums I minus 1, okay, times 26, okay, to the power of the length itself, right? And then we will be adding the new numbers. That's going to be the I plus length minus 1, okay? And then here actually we're doing a 26 to the power of 0, right? But since this thing is always 1, we can simply skip that, or I can skip it here, okay? Then same thing, if the age in scene return true, okay? And then scene dot add h, okay? Yeah, I think this should just work. Let's try to run these things here. Length, a typo, RENG GH TH length nums, okay, nums submit. Cool. So this one also passed. All right. Okay, cool. I think that's the last thing I want to talk about for this problem. I know it's a long videos, and if you have watched to this at to this moment, you're really like hard working guys, or like you're really trying to understand everything. Okay, even for this the implementation uh, of the hashing function, the rolling hashing. Even for this one, this is my first time implementing this rolling hashing mechanism, right? So the only reason we're doing the rolling hashing is we're trying to, I mean, improve this part from O of L, right, to O1. Okay, and in order to do that, we have to come up with a rolling hashing mechanism, and this is how we calculate that. Okay, cool guys. I think that's pretty much everything I want to talk about for this problem. Yeah, and you know, binary search plus a few improvements of the helper function. Thank you so much for watching the videos, guys, and stay tuned. See you guys soon. Bye bye.